Hello again. In this video, I want to take you through the first several pages of this packet that hopefully you have a copy of in front of you. If you don't, you can certainly follow along and take the high points down, but I'm guessing most of you, as you watch this, would have a copy of it on hand. This is the National Math and Science Initiative note packet on stoichiometry, one of the first topics of the year, and a lot of information that carries over from first year chemistry if you took that class. If you didn't, some really important things in here that will continue to be important throughout the year, and that you might notice at least early on here are things that others who were in the class that took chemistry already sort of have an advantage on because they've got so much more experience with it, but that you'll pick up on right away. It's really not that difficult of stuff to figure out if you dig into some practice and see some of the basic uses that we get, that kind of basic I guess tools that get used over and over in different ways. And it's really got a lot of connections back to Algebra 2 as well, so if you've had that class, that'll be a big advantage for you. But let's dig into it. right off the bat here, one of the first topics in stoichiometry is atomic mass, and probably even more importantly than that, average atomic mass. Average atomic mass, or atomic mass, basically is a way of looking at the atoms of a particular element in a way that's useful for us in class. And so as we look at a periodic table, so hopefully you've got a copy of the AP periodic table as well, all these numbers that we see on here. So for example, this one is pointing to neon 20.18, or carbon 12.01, copper 63.55. These are average atomic masses. And they have a use in a couple of different places, unique places in chemistry. Average atomic mass of the element. They're also known as what we call the molar mass of the element. And those numbers serve in both of those roles. The difference is average atomic mass is the average mass of one atom of, say, carbon, for example. And that's so the mass of one carbon atom is really tiny. We measure it in what's called the atomic mass unit, or the AMU. That's not a real practical way to measure matter, because we can't measure one or two atoms at a time. So typically we would use this same number in a much larger way, and you'll see more about that here in the next several minutes. And that's where we talk about it in terms of molar mass. Molar mass is measured in grams, and of course grams are something that we can easily go in the lab and measure out on an electronic balance and get 12.01 grams of carbon, for example, really easily. Okay. AMUs are impossible to measure. Grams are the convenient way that we have of using those same numbers from the periodic table, but in a way that's actually possible in the lab and not so small that it's beyond our comprehension. So more on that as we go. But where do those numbers come from? Well, back in the day, it's been quite a while now. I can't even tell you off the top of my head what the year was when the mass spectrometer was first put into use. But it's been around for quite a long time, longer than you'd probably think. And what it allows us to do is take a sample of matter and figure out in that sample how many atoms have a mass of, say, in carbon's case, a mass of 12 AMUs or 13 AMUs or 14 AMUs. Now, I'm not going to take you through the ins and outs of how a mass spectrometer works. The video link that I've written here at the top of the page on YouTube is a really good one that explains rather briefly but very well what a mass spectrometer is and how it works. And it's a video from Bozeman Science. It's quite good. I would encourage you to watch it. Not something I'm going to hold you responsible for being able to explain back to me, but it helps you to understand where the heck these numbers come from. And it's really quite a cool conquest of engineering to figure out how to do this with something on the size of an atom and to do it consistently and effectively. So I would encourage you to take a look at it. If you've never seen a mass spectrometer, and chances are you haven't seen one or learned about one. So watch that if you have a few minutes, about 8 minutes or 9 minutes, I think, and well worth your time. I won't go through all the ins and outs of how a mass spectrometer works here, because that video says it quite a bit more clearly and probably a lot more effectively than I would. Plus, it's got some great animations that explain how that device works. Okay. So what a mass spectrometer eventually gives us, though, is a distribution. And by that I mean it tells us how many atoms of a particular element have a given mass. So from that we can calculate the average atomic mass. Now I'm going to highlight the average atomic mass here. Average atomic mass being the thing that we're actually interested in using. Those are those numbers, again, over here on our periodic table. So the ones I highlighted earlier for copper and carbon and neon, the average atomic masses they don't represent one atom of each of those elements. They represent the average atom of those elements. So no atom of carbon actually has a mass of 12.01 AMUs. No atom of copper has an actual mass of 63.55. Those are the averages, and that's the mass that we're going to use for all carbon atoms, or for all copper atoms, or for any element at all, as their mass on the average. Because when we work with, say, copper, we're not working with a few atoms, we're working with trillions and trillions of them, and that allows us to treat the average as if every atom in that sample had that mass. Okay? So it's sort of a way of effectively and simply being able to work with matter without losing our minds in the mathematics. In any given sample, a mass spectrometer would tell us that there are probably 2, 3, 4, maybe as many as 8 or 10 different sizes of that element. So for example, here on page 2 of the packet, the mass spectrometer data is given for neon. So this is a sample of natural neon. And what the data points out here for us is that there are 3 different kinds of neon atoms. There's neon 20, neon 21, and neon 22. And the way we can tell that is by the peaks here on this little graph. Now, if you've taken calculus, and probably most of you haven't, but you learn about area under the curve. And so we would know that the amount of area here underneath the curve here, if we were to sort of shade this space in, would represent sort of the proportion of the neon atoms that have that mass. Now, we're not going to get into calculus, but it's pretty obvious here that in this particular graph, that the most common, I'm just going to clean this up, the most common size of neon is neon 20. This is the dominant one. There's lots of those. There are a few of these neons that have a mass of 22. And then there's just a teeny bit, okay, we'll say a tiny few atoms that have a mass of 21 for neon. So the most dominant atom of neon, the most dominant size of neon then is 20. Therefore, the average is probably pretty close to 20. But because there's some heavier ones, 21 and 22, the average atom of neon has a mass of just a little more than 20. Okay, so we can kind of gauge that just by looking at the graph. Lots of 20s, a few 22s, and just a very few 21s means the average mass, average atomic mass, will be somewhere just a little bit bigger than 22, or rather than a little bit greater than 20 AMUs. So just a little bit more than 20. We can see it drawn out another way here. The same sort of 3 spikes that we saw in our first graph are drawn out on the second graph. And we can again see that the most dominant one is 20. It's telling us that 91 out of 100, essentially, or 91%, if you want to think about it that way, okay, have a mass of 20. About 9% have a mass of 22. And then just a tiny little fraction of a percent, 0.3%, has a mass of 21. So that's basically like saying what? That's 3 out of every 1,000. It's kind of what that's saying. So very, very few neon atoms with a mass of 21. So it's the same data that was given on our first graph, but given here with actual numbers or percentages instead of sort of a relative comparison, which is what that graph allowed us to do without any real numbers. So this is a little bit clearer. But even here, again, we would say and expect that the average mass is slightly more than 20, but not much more than 20, because 20 is the most dominant, and about 9% have a mass bigger than that. Well, again, go back to your periodic table, check out neon, and we saw earlier that sure enough, right, neon has an average mass of 20.18. So yeah, the average is just a little more than 20, like we'd expect. Now that sort of data, like you see in those little spikes or those peaks on the mass spectrometer output here, allow us to calculate the average atomic mass of an element, or given the data, estimate it at least. What's the most likely average? Now the way we mathematically would do that is no different than how you would find a weighted average of any other quantity that you were studying, whether it be a test score, average test score for a class of 20 students or something, or any other weighted average, where there's a different number of students scoring a different score. And so in this case, the data is given to us here for a sample of copper. Right? So copper is vaporized and injected into a mass spectrometer. The results are shown. So this graph is much like, right, this second graph that we saw over here for neon, but the data for this one is for copper instead. And it tells us here in the problem that we're going to be asked to calculate the average mass of natural copper atoms. Specifically, it tells us also that the mass values for copper 63 and copper 65 are 62.93, which is about 63, but we can use the precise number when we have it. And for copper 65, the mass is 64.93, again, about 65. We're not going to use 63 and 65 because we have these really nice precise masses, 62.93, 64.93. We're going to use those instead. And I'll show you how to set this calculation up just real quick. So if we want to calculate, pardon me, let me switch back to pen here. If we want to calculate the average atomic mass, and that's our task here in this question, what you'll do is take the mass that we're given here and the percent distribution. So we see those over here in the chart. 69.09% have a mass of 63, or our copper 63 atoms, which we saw up here have a mass specifically or precisely 62.93 AMUs. So while they rounded on our graph over here to 63, it's actually 62.93. And the reason why it's not a nice whole number is because the way these numbers come about is that they're compared to the official standard atom, which is a carbon-12 atom. So the only carbon-12 is a perfect whole number. Everybody else is some decimal. That's pretty close to a whole number. In this case, they're very close to 63 and 65. And the 65 here would be actually 64.93. So those are the numbers we're going to use for those. Rounded off to the nearest whole on our graph, but not in our math because we don't need to round here. We want to keep our data as precise as we can. The other spike then on our graph is 30.91%, and that represents the heavier copper 65, as we call it, with a mass of 64.93 AMUs. So again, these would be approximately 63 and approximately 65, but because we have precise numbers, those are the ones we're going to use in our calculations. And from there, it's just punching it into your calculator, right? Now, remember with percentages, you want to punch those into your calculator just like you would any other percentage as a decimal. So in other words, 75%, we would treat that as 0.75, right? 10%, we would treat that as 0.10 or 0.1. So for our percentages here, we want to treat those as decimals as well. So that'd be 0.6909. We're basically just moving the decimal over twice, right? And the same thing here, 0.3091. So when I go to punch this in my calculator, those are the values that I want to use. Not the percentages, but written as a decimal, okay? So let's go over to the calculator and punch this in. I've got 0.6909 times 62.93 AMUs. Plus 30.91%, oops, now I went ahead and did it wrong anyway, 0.3091, 30.91% written as a decimal, times 64.93. And the average then comes out on my calculator to be about 63.5482. Now we're going to round that off to make it kind of match our other masses, about 63.55 AMUs. Per atom, okay? Per copper atom. That's the average mass. Now, I want to mention again, then we'll go on, that there is no copper atom out there with a mass of 63.55. That's just the average. Of all the coppers that we could go out there and find, the average copper, if we took a reasonable sample of them, would have a mass of 63.55. And that makes sense, right? Again, just one last look. Look at our data on our little chart here, and we'll see there's more of these. Okay, there's more of these 63s, and there are fewer of these 65s. So the average should be a little closer to this one, closer to 63, because there are more of those. And so the average comes out here to be 63.5 approximately, which is closer to 63 than it is to 65. So it makes sense, okay? Now, we can't go in the lab, as I mentioned before, and measure out atoms. We can't go out and measure out atomic mass units or count out a few copper atoms. So how do we use these kind of numbers in a useful way? Well, we're going to hear about the mole now. And again, if you've taken first year chemistry, the mole is going to be old news for you. You've used it a lot. But what it basically does is allow us to do something that's mentioned here, and that's counting by mass. Counting by mass is the idea that it's really impossible to count a lot of things out one at a time. And the example that's given here in this paragraph is that you wouldn't go to the grocery store and buy 5 pounds of sugar by counting out the grains. You wouldn't go into the store and buy 300 million grains of sugar. You'd go into the store and buy 10 pounds or 5 pounds. You wouldn't go into the store, as it says here, and buy 550 peanuts. You'd go into the store and buy a pound of peanuts or 2 pounds of peanuts. So we measure and we buy a lot of things by mass instead of it, by particles. We don't count out the number of grapes that we're buying at the store. We buy 2 pounds or 3 pounds of grapes. So there's a lot of those things that are like that. It's just not practical to go in and count out grapes at the grocery store. You might count oranges because they're huge, right? You might count out, say, cans of soup, but you're not going to count out apples, or rather, you're not going to count out grapes. You're not going to count out grains of sugar. It's just ridiculous. So a lot of smaller things we already are kind of used to counting by mass, by something larger. And we do that with our atoms as well, because we can't go into the lab and measure out certainly 1 atom. We can't go into the lab and measure out 1,000 atoms. So we go about it by measuring out and counting out a pound of peanuts or 4 pounds of sugar. In the chemistry lab, we can't reasonably go back in the lab and count out and work out 1 million copper atoms or 1 billion atoms of neon. It doesn't work. So what we do instead is we use a quantity of them. So instead of, say, buying a dozen of something, or a quantity like a dozen that we get used to using, and dozen is probably the most common word that we use that is a word that means a number. And it's mentioned here. Dozen means 12. Right? We're used to that. Everybody knows dozen means 12. And the word couple means 2. Those are words that mean quantities. Another one you might have heard about and used is the word score, as in 7 years ago. And maybe you know that a score is 20. In the words of Lincoln, it was 20 years. 4 meant 80 years. So 87 years ago, 7. So a score is 20. Even the word sort of like the word decade or century have numbers attached to them. The word gross, before it meant disgusting, meant 144 of something, essentially a dozen. So there are words, a lot of them out there actually, that mean a quantity. And dozen is 1, couple is 1, baker's dozen, hopefully you know, means 13, and those sort of things. The word that we're going to introduce here, the word that we're going to start to use a lot of, is this word, the mole. Now, I want you to go in your little brain there. It's firing on all cylinders here. I want you to go in your brain and find the section of your brain where you keep words like dozen and words like gross or words like decade or couple or century. And you think about another word to stick in that box, and the word is mole. Mole means 6.02 times 10 to the 23rd of something. 6.02 times 10 to the 23rd of something. And that is what we call Avogadro's number. Avogadro is a fellow, he's an Italian. Avogadro was a physicist who, with a team, was among those first people to figure this number out. And you can read more about that story. He actually used electric charge, and it was a pretty cool experiment. I won't get into it here. But Avogadro's number is 6.02 times 10 to the 23rd. Now, you don't need to memorize that number. It's on your formula sheet. Okay, you've got an official AP formula sheet. Okay, over here on the formula sheet, Avogadro's number is listed right up here. 6.02 times 10 to the 23rd per mole. Okay, is what that means. Per mole. And mole is abbreviated as MOL, so that's not a typo, that's just the short version. So 6.02 times 10 to the 23rd, say atoms per mole, or molecules per mole, or bananas per mole of bananas, but boy, that would bury the country in bananas. So 6.02 times 10 to the 23rd is a ridiculously large number that we couldn't reasonably count. You couldn't go in the lab and measure out 602 billion, million, or whatever the heck this number is, atoms of, say, carbon. But conveniently, Avogadro and others have figured out for us that 6.02 times 10 to the 23rd atoms of carbon represents 12 grams of carbon. Okay. Or, on the periodic table, 20.18 grams of neon. And any of the other numbers that are on the periodic table. So back over here to the periodic table, like I mentioned earlier here, the molar mass, in other words, the mass of 1 mole of any substance, is that number on the periodic table. So 1 mole of carbon, 12.01 grams of carbon. 1 mole of copper, 63.55 grams of copper. So 1 mole of any element is simply the number of a number of grams of that element, of the number that you see on the periodic table. So a mole of, say, lead would be 207.2 grams. And the number is unique, as you can see on the periodic table. It's unique for each element, but all of those things represent 1 mole of the particular element, and they represent 6.02 times 10 to the 23rd atoms of that element as well. Okay, you're going to see more as we go here, but those are some handy equality statements that we'll use a lot of as we get into some mole conversions. Now, as you hopefully saw in an earlier video about conversions, as simple as like grams and kilograms, liters and milliliters, it's a simple matter of dimensional analysis, which is a term you may or may not be familiar with, but you've probably done this before, even if you've never called it that. And it's something that they do a lot of in Algebra 2 these days, that you might have heard of as well. What you'll find here on the next page of your packet are going to be the tools that will allow you to do dimensional analysis or conversions between these different units for things related to the mole. Now at the center of this thing you'll see the mole. Right here in the middle, the number of moles is like the hub of this thing. But all the way around it we see these different things like particles. This would be atoms. Pardon me, I keep leaving myself in highlighter mode. This would be atoms or molecules or ions or formula units or any other kind of word that would represent particles. Okay, so there you see Avogadro's number, 6.02 times 10 to the 23rd. That's going to be the tool that'll help us get from moles to particles, okay, through that arrow on the right side there. And we can do the same thing with mass. So on the periodic table, we can look up the molar mass of an element. There it is. And that's, as you see here, in grams per mole. And that's the tool that we can use to go back and forth between the number of moles of an element and the mass in grams of that element. So these two little connections in the middle with the arrows are the tools that allow us to work between moles, grams, and particles, any combinations of those. Now the things that are on the top and the bottom, sort of the north and the south in this picture, are tools that we'll come up to later. So you won't see those right away, but they're going to be coming shortly. Okay. Let's just work on a question or two on this packet here and see if we can't show you how to use some of those tools. All right. Now exercise 2 on this packet as it's printed here, it talks about an element that I'm actually not even sure if I'm pronouncing this right. I think it's Americium or Americium, but it's named after America anyway. And it's an element it's a synthetic element. So it says here this is an element that does not occur naturally in the world, in the universe. But we can make it. So we make it in a device called a particle accelerator, which is pretty amazing and huge. Won't get into that here. But they're asking us simply to calculate the mass in grams of a sample. Mass in grams of a sample containing 6 atoms. So that's what we're going to start with, 6 atoms of the element Americium or Americium. Now that element is abbreviated as AM. That might be an element you've never even heard of or used before. It's over here in the periodic table. AM is down here at the bottom, so it's going to be this guy that we're going to use. All right, element number 95, one of the synthetic elements. So more on that in a minute, okay? But the question asks us to convert and get from 6 atoms to grams. So we need a way of eventually getting from atoms to grams. Now I'm going to go back up here for a minute to my map, okay, this mole map as it's called, and make sure I've kind of charted out a course, right? Just clean things up here just a minute so we kind of get a fresh look at this thing. We've got atoms in this problem, right? We've been given 6 atoms. And what we're being asked to find is over here. How many grams will that be? Well, it's 2 steps. We're going to convert from atoms to moles, and then we're going to convert from moles to grams. Essentially, we're going to be working our way through 2 of these arrows. We're going to be working our way through this step, and we're going to be working our way through this step. Okay? So it's 2 steps away. From atoms to moles, and then from moles to grams. To go from atoms to moles, you can see they've pointed at us using this 6.02 times 10 to the 23rd, okay? That Avogadro's number. So we're going to use that number here in just a moment. And then to get from moles to grams, we're going to need to use the molar mass, which comes from the periodic table. So let's see if we can't plug those numbers in here and make this thing work with a conversion. Okay? Now I'm going to want atoms to cancel out. So I'm going to say that 1 mole of this element contains 6.02 times 10 to the 23rd atoms of this element. And again, that's true for any element. 1 mole of an element is 6.02 times 10 to the 23rd atoms of that element. Now, if I stopped here, right, atoms would cancel out, and I'd be left with moles. But the question doesn't want moles. The question wants grams. So we need to go one step further. I'm just going to hang it off the end of this problem and go one step further. I need a way to get from moles to grams. And again, that's going to be our molar mass step. So in this first step, we used Avogadro's number. In this next step, we're going to use molar mass. And those are sort of two truths. If you've seen one of my videos before, you know I like the idea of truths or equality statements. 1 mole of Americium is 6.02 times 10 to the 23rd atoms. Well, we need another equality statement here. And it's as simple as 1 mole of that element has a mass in grams of what? Well, if you don't remember, take a quick peek again. Back to the periodic table, we're looking at, here it is, 243 grams per mole. Okay? So that's the number we're going to use in our problem to make our final conversion. 243 grams per mole. And then I'm ready to punch it in my calculator. Okay? So I'm going to go back over and do that. 6 atoms times 1, don't need to punch that in, divided by 6.02 times 10 to the 23rd atoms times 243. And again, you'll see I usually leave the ones out because we don't need them. It's just another chance to make a typo. I do want to point out, though, and the answer that we should end up with here is 2.42, you can see on the calculator there, times 10 to the negative 21st. Don't forget that little power is over there because that's obviously really important. So 2.42 times 10 to the negative 21st grams of our element. Okay, that's my answer. I just want to double check though, make sure in your calculator that you were able to punch this in within scientific notation properly. Now you may have a button like I do here that's an EE button. You may have an EE button. The TI-84s have that. You may have an EXP button. A lot of scientific like TI-30s and other common scientific calculators have those. Some Casios that I have in my room have those. You may also see a button that says times 10 to the x, a button that looks kind of like that. But you'll need a button that does one of these things. And sometimes, as you see on mine here, it's a shift function. So I have my EE as a shift function. It's above my comma here. And so you need to find that button behind your button. And you have to use this at a number of places throughout our calculations and our math, whether it's here or when we get to acid-base chemistry, you're going to have to be able to use it. So make sure you know where that button is on your calculator and that you know how to punch numbers in with it properly. So 6.02 in this problem times 10 to the 23rd became 6.02, and then I used my little button here, this guy, E, whatever your E button is, 23. And my calculator actually displays it that way. So when you see this E, okay, pop up in any calculations that I write out like this, or you see me mentioning it, it's going to be your E button. Okay, your E button is one of these choices probably. And if you can't find yours on your calculator and you have a scientific calculator, send me a picture. Even just email me a picture of your calculator screen or your calculator with all the buttons, and I'll try to make sure you know where to find it then and how to use it right. You can get around it, but it ends up causing you a lot of extra work, and it actually opens the doors to a lot more mistakes if you don't use the E button properly. Okay, so hopefully you know where that button is on your calculator. It may have been a while since you've used it much, but we'll get you back up to speed. All right, let's see if we can get through another problem here. Aluminum, question 3. Aluminum is a metal with high strength to mass ratio, resistance to corrosion. It's used for structural purposes. That's all background information about aluminum. It's fine and good. What they want here is 10 grams of aluminum to end up in moles and the number of atoms. So we need to get from 10 grams to moles and then to atoms of aluminum. Well, that's kind of like our mole map from before. We're going to get to moles by converting grams and moles, relating them to each other. And I go to my periodic table for aluminum. 1 mole of aluminum has a mass of how many grams? Well, I think you'll find it over here. Okay. Here it is. 26.98 is our molar mass of aluminum. That's grams per mole. So back to my math. 26.98 grams of aluminum in every 1 mole. That's an equality statement. All right. Now, if I stop there, I'm going to have moles, and they do want, in this question, me to have moles. So let's go ahead and get an answer there. So 10 times 1 divided by 26.98 gives me 0.371 moles of aluminum. So there's my first answer right there. That's this guy, moles of atoms. Now, we do need to go one step further, though, because they also wanted the number of atoms. So let's go ahead and give them that, too. I know that 1 mole of any element, including aluminum, contains 6.02 times 10 to the 23rd atoms per mole. And remember, that's the number that's on your formula sheet, so don't feel like you have to memorize it. But if you have the ability to store constants as letter shortcuts in your calculator, I would certainly encourage you to do that. Right. So now to get the answer for my atoms, I just need to multiply my previous answer, which is still in my calculator there, times 6.02 times 10 to the 23rd. So I'm going to take my answer from the previous question times 6.02 E23. All right, and there it is, 2.23 times 10 to the 23rd. Okay. 2.23 times 10 to the 23rd aluminum atoms. And you'll notice my version here on the screen has the answers in the corner. And kind of know when we got to them at the end and make sure I don't leave you any wrong answers and not notice by mistake. Your version may or may not have those answers in there, so you maybe won't notice that printing on yours. All right, I'm going to leave number 4 for you to try, right, to do. And what I'd like for you to do in that is pause me here in a moment. Pause me, and then I'm going to work it out while you pause me, and I'm going to pause my recording too, and then it'll come back in a minute and let you check yours. So you pause me here in just a moment, and then when you're ready, just start the video again, and it'll show us the answers. All right. So pause me in 3, 2, 1. Okay. Hopefully you paused me for a moment there, worked this problem out, and got the 2 answers that you see here highlighted on the page for me. Now, those are the same answers in the corner here in the answer I have in the box, but notice your calculator may not switch over to scientific notation quite as quickly as some do. The one that I have up my calculator on the screen here switched over and gave us the answer here, 8.31 times 10 to the negative 4th. Your calculator might have given you 0.0008305 It may have given you all that. That's the same thing. Yeah, that's perfectly fine. A lot of calculators won't switch over to scientific notation quite as quickly as mine did. And so if you had for an answer 0.00831, that would be the same thing as what I have, just written in scientific notation with mine. And then the answer that they had over here at the end in the box was 4.89 times 10 to the negative 2 grams. My calculator gave me 0.0489. Same thing again. And if you're not real comfortable with getting back and forth between scientific and typical notation, let me know, and I'll try to walk through it a little bit more with you, or connect you to some resources online that will help you understand it better. Okay. Now, that's as far as I'm going to go with this video. I'm going to pause this and this video now and pick up with another one for the next few pages. We're trying to get through the end of page 7 with the next video. And then we'll pick up after that in a future video. But for now, I'm going to say goodbye on this video and let you work further on. As always, as soon as you're ready to go further without any help, go for it. Don't sit and watch videos and listen to me when you don't need to. But feel free to grab those videos, open them, and then just jump into the middle of them and find the spots where the answers are done and see how much you got correct or if you had any mistakes. And then let me know where those trouble spots are if you can't figure out what you did wrong. Okay? Don't listen to me any longer than you have to. And that probably goes without saying, but I'm going to point it out anyway. Okay? Thanks for listening, and I'll see you in the next video.